Let us continue with our discussion on solving some more numerical problems. And today we will further discuss on calculation of changes in entropy under different conditions. Let us first take up this question, which is calculate the change in entropy when 200 gram of water at 0 degree Celsius and in the second experiment ice at 0 degree Celsius is added to 200 gram of water at 90 degrees Celsius in an insulated container. If we look at the statement very carefully, what is being done is, in one case we are adding 200 gram of water which is at 0 degree Celsius to 200 gram of water which is at 90 degrees Celsius. So, in this case you are just mixing two liquid forms of water which are at different temperatures. And in the second case, that is part B, what we are doing is we are adding 200 gram of ice at 0 degree Celsius and this is being added to 200 gram of water which is at 90 degrees Celsius. The point to be noted here is, here we are adding ice to water. So, therefore, there has to be a phase change in this mixing and we have to account for that. But first let us take up case number 1, when we are adding 200 gram of water at 0 degrees Celsius to 200 gram of water at 90 degrees Celsius. So, obviously, one part of the water which is at 0 degrees Celsius will be gaining heat and the other part of water which is at 90 degrees Celsius will be losing heat, and overall heat change, heat gained plus heat lost has to be 0. So, that is what we are going to now use the information on. Let us say we are taking N1 moles of any substance and let us say the heat capacity is Cp, I will put Cpm, into T final minus T initial of substance 1 plus N2 times Cpm if it is the same substance Tf minus Ti2 has to be 0, that is heat gained plus heat lost has to be equal to 0, and the heat gained or heat lost is given by this formula, N is number of moles times heat capacity times the temperature difference. Now, since here the heat capacities are same, these will get cancelled. So, what we have N1 times Tf minus N1 times Ti1 plus N2 Tf minus N2 times Ti2 has to be equal to 0. Let us take Tf outside. Inside what we have N1 plus N2, this is going to be equal to N1 Ti1 plus N2 Ti2. Rearranging this, we can calculate the final temperature as N1 Ti1 plus N2 Ti2 divided by N1 plus N2. Now, let us go to the slide. This is the formula Tf is equal to N1 Ti1 plus N2 Ti2 over N1 plus N2. This is the formula that we just derived. Now, if you mix equal amounts, for example, in the given question, you are adding 200 gram to 200 grams. So, same number of moles. Then N1 is equal to N2. If you put N1 is equal to N2, this solves out to Ti1 plus Ti2 divided by 2. That is, the temperature will become half of the addition of 2. Since one sample of water is at 0, other sample of water is at 90 degrees Celsius divided by 2, and this 90 divided by 2 is 45. In Kelvin, this will turn out to be 318 Kelvin. So, you see what we had, we had water at 0 degrees Celsius, we had water at 90 degrees Celsius, and the final temperature is 318 Kelvin. Since we know the final temperature, we can calculate the entropy change by using the well established equation that we derived earlier. That is, for the first sample of water, delta S, for the first sample, it is N1 times molar heat capacity into log T final over T initial, plus for the second sample, N2 times CPM times log T final over T initial. And in fact, if you combine these two logarithmic terms, this is, N1 is equal to N2. So, if N1 is equal to N2, N will come out, or N1 you can substitute, CPM will come out. So, it is log A plus log B times log A plus log B is equal to log A into B. So, when you combine, the final form is N1 into CPM into log T final square over Ti1 into Ti2. This is because N1 is equal to N2. So, now if I have the information on the number of moles, molar heat capacity and initial and final temperatures, I can easily calculate the value of delta S. The heat capacity of water is 75.3 joules per Kelvin per mole, and we know how to calculate number of moles. It is weight divided by molecular weight, and once you substitute these numbers where Ti1, see it was at 0 degrees Celsius. So, you put 273. For second sample it was 90 degrees Celsius. So, we put 363 and final temperature is 318 Kelvin. And when you solve it, the answer comes out to plus 16.9 joules per Kelvin. Now, we take a look at the second part. Now, you are adding 200 gram of ice to 200 gram of water. So, therefore, what is happening? We are taking 200 gram of ice solid form, which is at 0 degree centigrade, and this is being added to water same amount 200 gram, which is at 90 degree centigrade. Now, since we are adding to ice, first of all, this phase equilibria will be set up. That is, the solid form has to be molten to liquid form, and some heat will be required for this phase transition. How do we calculate this heat required? This will be number of moles into CPM, molar heat capacity, into T final minus T initial. Let me put delta T. From where this heat will come? Number of moles times enthalpy of fusion. The enthalpy of fusion, we know the value of water, and if we know the molar heat capacity of ice, we can easily calculate how much is the change in temperature. Now, let us go back, look at the slide. Heat required for melting N times delta H fusion, N is 11.1 mole and delta H is 6.01 kilojoules per mole, it turns out to be 66.7 kilojoule. So, by using this information and the formula that we just derived, delta T is equal to Q by CPM, which is same as this. From here we write delta T is equal to N times delta fusion H0, because it is a constant pressure, I can write it as Q also, divided by N times CPM. So, you can include N into this, or you can just cancel N and use 6.01, whatever way you want to use. Delta T by this calculation comes out to around 79.8 Kelvin, which is approximately 80 Kelvin. The change in temperature is AT. It does not matter whether you count it in degree Celsius or you count it in Kelvin, because the change delta will remain same. Initial temperature was 90 degrees Celsius and the change in temperature is 80 degrees Celsius or 80 Kelvin, which is same. Therefore, the final temperature is going to be 90 minus 80, which is equal to 10 Kelvin or 10 degrees centigrade, not 10 Kelvin, 10 degrees Celsius. So, up to this, that is up to the point when ice has molten into liquid water at 0 degrees Celsius, the temperature of the water which was at 90 degrees Celsius has fallen down to 10 degrees Celsius. So, there is an entropy change. How do we calculate that entropy change? Let us take a look at. Entropy change for the phase transition is equal to enthalpy of fusion divided by the freezing point, that we have discussed many times. This is the entropy change associated with the melting of ice at 0 degrees Celsius. And then, since the final temperature is 10 degrees Celsius, we have to now calculate the entropy change associated with the sample of water which was earlier at 90 degrees Celsius. And for that we will use NCP log T final over T initial. T final is 283, which is 10 degrees Celsius, and T initial was 90 degrees Celsius, which is 363 Kelvin. So, once you substitute these numbers for enthalpy of fusion, number of moles, heat capacity, the change in entropy is plus 35.3 joules per Kelvin. This is the change in entropy associated with the melting of ice and the decrease of temperature of water, which was from 90 degrees centigrade, it has come down to 10 degrees centigrade. So, what you have now? you have water at 0 degree Celsius, water liquid form at 0 degree Celsius, and you have water liquid which has decreased in temperature from 90 degree Celsius to 10 degree Celsius, 200 gram of each. So, when these two further mix, the final temperature by the same arguments that we just discussed, because the number of moles are same, the final temperature is going to be the average of the two, which is 0 plus 10 degree Celsius divided by 2 or 278 Kelvin, which is 5 degree Celsius. So, therefore, now I can easily calculate the entropy change which is associated with 200 gram of water which was at 0 degree centigrade and reaching 278 Kelvin, and 200 gram of water which was at 10 degree Celsius and it is now reaching 5 degree Celsius. So, that is why N1 CPM log Tf over Ti1 plus N2 CPM log Tf over Ti2. When you make further rearrange this, you get this expression. Ti1 and Ti2 both are known, because initially one of the sample was at 0 degree Celsius, other was at 10 degree Celsius and giving a final temperature of 5 degree Celsius. Converting into Kelvin, and after substitution of the values, we see that the change in entropy now is 0.27 joules per Kelvin. Therefore, the total entropy change is the entropy change in part 1. This part 1 means this is associated with the melting of ice and the lowering of temperature of water, 200 gram of water from 90 degree centigrade to 10 degree centigrade, and this contribution is now when the water at 0 degree centigrade is further mixing with water at 10 degree centigrade, reaching a final temperature of 5 degree centigrade, the total delta S is plus 36 joules per Kelvin. So, although the problem is bit lengthy, but it does explain how to account for the changes in entropy. Remember that during the process of mixing of ice with water, which is at higher than room temperature, the first step is that the ice has to melt, it has to go to liquid water, and that is a phase transition, and we should not miss any phase transition. This is a point which is worth remembering, that while calculating the changes in entropy, if there is any phase transition, let us not miss that. We must calculate the entropy change corresponding to phase transition plus the entropy changes which could be due to changes in temperature. Now, let us take another type of question, which is calculate the maximum work and maximum non-expansion work that can be obtained from freezing of supercooled water at minus 5 degree Celsius and 1 atmosphere. The densities of water and ice are 0.999 and 0.917 gram per centimeter cube respectively at minus 5 degree centigrade. Let us try to examine the question and see what is being asked and how we should approach answering such questions. We are asked to calculate the maximum work. Maximum work means we have to calculate delta A, and then we have been asked to calculate maximum non-expansion work. Maximum non-expansion work means we have to calculate delta G. So, this should be very clear that what should we calculate for maximum work and what should we calculate for maximum non-expansion work. it is freezing of supercooled water at minus 5 degrees Celsius and 1 atmospheric pressure. Take a look at the slide. Let us first calculate the maximum known pressure volume work. The reason for calculating the maximum known pressure volume work first is that if we have the information on delta G, it is easy to then calculate delta A from the given information. And to calculate delta G, we need information on delta H and we need information on delta S at minus 5 degrees centigrade. The question is now, how do we get the information at minus 5 degrees centigrade? Let us see. Delta H at any temperature, let us say, I can calculate from the knowledge of delta H, let us say at freezing point, plus delta Cp into T minus Tf, where T is any general temperature. Now, the second information that we need is on delta S. Delta S at any temperature, I can calculate from the knowledge of delta S, again let me use the freezing point, plus delta Cp log T by Tf. Please remember that this is the entropy of phase transition. So, therefore, I can use delta S at any temperature is equal to, this will be what? This will be enthalpy delta H at freezing point, which is enthalpy of fusion, divided by the freezing point, plus delta Cp log T by Tf. Now, I make use of this equation, delta G at any temperature is equal to delta H at any temperature minus T into delta S at any temperature, and I will now substitute delta H and delta S at any temperature. What do I get? Delta G at any temperature is equal to delta H at any temperature is delta H at freezing point, that is enthalpy of fusion, plus delta Cp into T minus Tf minus T delta S minus T into delta S, I will put the entire thing over here, which is delta H at Tf over Tf plus delta Cp log T by Tf and now if you further rewrite delta G at any temperature T is equal to delta H at Tf, if I take out as common, it is 1 minus T by Tf from here and here, then plus delta Cp, let us take out common, it is T minus Tf minus T log T by Tf. This is the equation that can be used. Now, please remember that we are talking about that this T is minus 5 degrees Celsius and this is the freezing point, right. So, we have to calculate delta G, which is obtained from freezing of supercooled water at minus 5 degrees Celsius. It is a freezing of water, right. So, the equation to be used now is actually negative of this, because here what we are using is this T is any general temperature, T is this Tf is the freezing of water, a freezing point of water. So, maximum work that can be obtained from freezing of supercooled water at minus 5 degrees Celsius and 1 atmosphere is actually going to be negative of this, and that is why the equation that we are using over here is actually negative of what we have derived. It is the same equation that we just derived, but with a negative sign, because we are talking about freezing liquid to solid. Once you substitute the numbers, the answer comes out to be minus 0.11 kilojoules per mole. Right. So, let us now comment on this minus 0.11 kilojoules per mole, that is the maximum non-expansion work, because delta G is a measure of maximum non-expansion work, which is equal to minus 0.11 kilojoules per mole. Now, we have the information on delta G and it is easy to calculate delta A. How do we do that? G is equal to H minus Ts, which is equal to U plus PV minus Ts. U minus Ts is A. So, therefore, G is equal to A plus PV. This allows me to write A is equal to G minus pressure into volume, and since pressure is constant, I will write delta A is equal to delta G minus P times delta V. And since mass is equal to volume times density, so I can write now delta A is equal to delta G minus P. If I know the molecular weight, what I need to know is 1 over delta rho. Delta rho is the density. We are talking about freezing. So, therefore, what we will do is we will substitute for the values. Liquid to solid, that is what we are talking about, and therefore, delta density has to be 1 over density of solid minus 1 over density of liquid, and minus 0.11 kilojoules per mole is the value of delta G. Pressure has to be in pascals, and molecular weight of water is 18.02 into 10 raised to power minus 3 kilogram per mole. So, we have to take care of the units and then put the densities of ice and density of liquid water. The answer still comes out to be minus 0.11 kilojoules per mole. So, you see both delta A and delta G are coming out to be minus 0.11 kilojoules per mole. So, therefore, the comment is both maximum work is in terms of delta A, and maximum non-expansion work, which is delta G, are about 0.11 kilojoules per mole each. So, this is the amount of work which is available from freezing of supercooled water at minus 5 degrees Celsius. So, I hope that these examples have cleared several questions that might have arisen when we were deriving these equations, and the application of these equations make us understand these concepts in a better way. We will further continue solving numerical problems in few other sessions where the concepts of delta G, delta A be again used. Thank you very much.